MSR is located in Seattle and still manufactures much of their gear at their SOTO headquarters. You're probably familiar with their backpacking and mountaineering gear, like stoves and tents. What's interesting though is they also make excellent winter backcountry tools like probes, shovels, and saws, as well as ski touring poles for both backcountry skiing, snowboarding, and snowshoeing. Behind their designs are passionate engineers and scientists who strive to create better solutions to the real world needs of backcountry adventurers. Because of this, their designs are simple, functional, and reliable. Their philosophy is to give you everything you need and nothing that you don't, so that you can trust your gear when you need it the most. You can check out their winter equipment at msrgear.com. So our first presenter this evening is VandenBos. Ben is an avalanche forecaster at the U.S. Forest Service Sawtooth Avalanche Center located in Ketchum, Idaho. After riding lifts at Bridger Bowl during his youth, Ben expanded his vision and embraced the rest of the mountains that surrounded his hometown of Bozeman, Montana. He earned a BS in geology at the University of Montana in Missoula, where he also developed the masochism required for long approaches to questionable skiing and climbing while exploring the Bitterroot Range. In the following years, supported by off-season work as a geologist, Ben focused his curiosity on the study of mountains and snow. His presentation tonight is entitled Earthquakes and Avalanches. Ben, thanks for joining us this evening. I'm turning it over to you.
All right. Thanks a lot for that introduction, Scott. Can you hear me?
Yep.
All right. Go ahead and get this started. See if we can not have any technical difficulties while we do. Let's see. How does that look to you guys? Can you see that?
Yeah, it looks great, Ben.
All right. Well, big thanks to Scott for that introduction and everybody at NWAC for putting this on despite the ongoing challenges posed by the global pandemic. I think it's a great opportunity for folks who may not necessarily be exposed to this sort of stuff to tune in virtually. And yeah, I think we're kind of trying to find the bright spot on the horizon despite plenty of darkness around. So hopefully that continues. I'm here privileged to be here. I'm glad to be able to talk to you guys about a pretty unique event that we had occur in our forecast area in central Idaho in about March of this past year. If you can read the title, you can see that it's about an earthquake. So I'm going to spend about a minute talking about earthquakes here before I launch into it. Here we are kind of looking at the rough geologic setting of you folks there in the Northwest. You can see the Cascade range of volcanoes there, and then this big the Juan de Fuca plate, which is subducting underneath the North American plate. Earthquakes occur where plates like this meet, and as they kind of slowly build up stress on those fault surfaces, and then they rupture when that stress builds up to a certain point, and you get what's known as an earthquake. Earthquakes occur in kind of a sequence, and they're moderately predictable in bulk, surprisingly, but not in specific. So we can say certain things about a fault, about the size of earthquakes that it might generate, about how frequently they happen, and those sorts of things. But predicting a specific earthquake at any given time is actually challenging to impossible, depending on who you want to ask about that. To set the scene for you here, we're looking at northwestern United States. We've got Idaho outlined there, and those colored polygons are our forecast zones for the Sawtooth Avalanche Center. Stanley and Ketchum are labeled on the map there for folks who have been through the area and have some familiarity. And there's a look at where the epicenter of this magnitude 6.5 earthquake that occurred was. I'm going to tell you this story of the earthquake in a couple of parts, kind of a past, present, and future sort of setting. We'll jump around a little bit as it makes sense. But to set that scene, let's look at a video I took just a couple hours before the earthquake happened, about 10 miles southwest of what would be the epicenter.
We're
exactly where we are, and what you can see is almost nothing. You can see there's a rock right there. I can see my ski poles, a couple trees, and yeah, that's what I got for you. Here we go. As Avalanche forecasters, we create a lot of photos. We take a lot of videos trying to explain to people what the conditions they might find are like. A lot of those end up as duds, end up in the trash, and this is one that I pulled out of the trash and ended up doing a pretty good job of setting that scene. But before we dive into the earthquake itself and the storm that surrounded it, I want to jump back a little bit to our early season week layers, knowing that the past is prologue to the present and the future. Let's take a peek at that. Here we're looking at a couple images of our snowpack. This is the snowpack in the Sawtooth early season of last year. We had a really well-developed layer of depth hoar that we buried around Thanksgiving. You can see that in both of these. And we also had a couple of layers of widespread surface hoar in our area. Surface hoar produce some pretty interesting avalanches, but they're not really in the scope of this presentation. So we're going to focus on that depth hoar. I'll show you a video here in a second of me doing a propagation saw test, a stability test on that depth hoar. As we were watching that layer develop, watching the slab over it develop, and becoming increasingly worried by it. In these tests, you're running your saw along the weak layer. You can see the kind of that gray depth hoar underneath, a little bit whiter snow on top. And you're starting this fracture and you're seeing how much of the fracture you need to generate before it will propagate to the end of the column. As you can see, I'm cutting less than a third of the way up the column here. I'm getting pretty crisp results every single time I do this. And it's telling me and it's telling us at the Avalanche Center that we've got a problem to look out for the future. And we didn't have to wait terribly long to see that problem rear its head. And we're looking at a kind of a northeast aspect here of Williams Peak in the Sawtooth. And if you look closely, kind of in the center bottom of the image there, you can see a series of crowns. Those crowns are about a little over a half mile wide, ranging up to 10 feet thick in places. And these were the result of a big storm that occurred and buried that weak snow near the ground that we had. In about a week, we had well over 3 feet of snow, 3 inches of water, and there's one kind of pretty intense period of precipitation towards the end of that seemed to set off this widespread deep slab cycle. According to folks who've been in the area for quite some time, is the most widespread deep slab avalanche cycle in the institutional memory for their guiding operations. For us at the Avalanche Center, there were crowns like this everywhere, which is somewhat uncommon in these mountains. Usually they have a bit more of a stable, moist snowpack, a little more like what you guys are used to dealing with out there on the West Coast. And then in the time following this big avalanche cycle and this big storm, things really quieted down quite a bit. We're looking at a graph of snow depth here on the top, snow depth at a weather station that we have in the Sawtooth. You can see on the far left, we're in late January and there's about 4 feet of snow on the ground over there. And as we slide off to the right, we stay at about that 4 feet, 4.5, maybe up to 5 feet of snow for 2.5 months really before we have any major storms. So that time period's pretty quiet. There's some spikes of avalanche hazard, spikes of danger, but really there's not a whole lot going on. Along the bottom there, you can see a little graph of our danger ratings in this zone during that time period. You can see we spent nearly 3/4 of that time at moderate. The other quarter was at low, aside from those couple of days of considerable hazard that we had, generally caused by little storms, little spikes in precipitation and increase in wind speed. And then right out there near the end, you can see that jump caused by this big storm that happened right at the end of March. At this weather station, we only got we got less than 2 feet of snow, but it's generally a kind of a poor indicator of upper elevation snowfall, and it's also south of where the main snowfall was hitting. But it gives you a pretty good sense of what we were looking at. And And so all of this is leading up to the event of interest, March 31st, 2020. At this point, we're 2.5 months since the last major storm in our area. We're 2 months out from first confirmed cases of COVID in the US, 2 weeks from the start of lockdowns in major cities, and the rates of COVID are absolutely exploding locally in Idaho for us. At a certain point during this period, we actually surpassed New York City for rate of COVID infections. So we're in I guess the point I'm trying to make is that we're in a pretty exciting time, even if the snowpack wasn't terribly exciting. And then the storm arrives. What we're looking at here is my a paragraph from my forecast discussion that morning, and I'll quick read it out loud to you. But I think it does a pretty good job giving you a sense of my thought process revolving around this storm, without any indication that perhaps an earthquake was going to occur during it. Today's the first day in 2.5 months that we have high danger in our forecast area. The ongoing pandemic reminds us that the world can shift underneath your feet. The storm in progress should remind you of the same. It's been a weird winter to say the least, one marked by an overall lack of stability, long periods of overall lack of snowfall, and long periods of relatively stable conditions. Today is different. If you choose to go out into the backcountry, be prepared to deal with a full spectrum of midwinter avalanche hazards. Dial back your ambitions and build a wide safety margin into the way you travel in the mountains. I think it's pretty apparent that we at the Avalanche Center were worried about what was happening, and we really wanted people to be aware of, not just the hazard posed by the storm, but the hazard posed by the ongoing pandemic as well. But that was not those two weren't the only problems we were to have that day. I issued the avalanche forecast that morning. I spent a little time looking at weather, watching weather roll in from remote weather stations, and then decided that I wanted to do what I normally do, which is go out and see if my forecast had verified. And I headed towards the northern end of the Sawtooth, the Banner Summit area, where I'd expected precipitation to be at its most intense. Got there, parked on the highway. There was a lot of snow on the highway, feet and feet of snow on the highway. And then I broke trail, kind of mid-thigh trail breaking up to the top, kind of a small point known as Copper Mountain up there. And I was able to look into one sizable starting zone, really the only one that I was able to approach with any degree of safety, and noted this big crown. It's a couple feet thick, a couple 100 feet wide. Pretty sizable avalanche occurring within the new snow. This happened maybe 3:30 or 4 o'clock in the afternoon of that day, and it was pretty obvious that we'd reached the breaking point. There were large natural avalanches occurring, even in the absence of the earthquake. And when I got back to my car, this is what it looked like on the road. Pretty much plowed in and nobody else in sight. I'd go to drive back to my house that night, and as I drive back into service, the text messages start rolling in. Lots of, "Are you okay? Did you feel that?" Those sorts of things. It took a minute for me to really orient to what had happened, but what had happened was a magnitude 6.5 earthquake, and it had occurred just north of where I had been skiing that day. And I immediately launched into one of the things that I enjoy doing the best, and one of the things that we're best at the Avalanche Center, which is making observations of avalanche activity and trying to make sense of the winter world around us. We were able to put together a pretty interesting database of the avalanches that occurred in the aftermath of this event. As far as the directly observed avalanches, we had nearly 500 of them, and they're indicated in this photo here, or in this Google Earth image. You can see those red lines are all crowns. And to give you a little sense of scale, there's the town of Stanley. It's about 40 miles from the epicenter there in the far right, down towards the south end of the range. And yeah, clearly there are crowns, basically crowns everywhere. This earthquake cycle, or the avalanche cycle following the earthquake and concurrent to the earthquake, produced just an absolutely huge amount of avalanche activity, but a lot of small avalanche activity. Most of these slides that we observed along the range front here were maybe D2 or D2.5 at the biggest. There were some D3s in there, but most of them were relatively small avalanches because they only involved the new snow that had fallen. Part of the reason behind that was that we had that, as I mentioned a bit earlier, we had that big deep slap cycle that seemed to flush quite a bit of the depth hoar that was near the ground and squish the depth hoar that wasn't near the ground, or that didn't get flushed in avalanches rather, and improve stability a bit because of that. The other way that we looked at avalanches was we partnered with Montana State University and a guy named Zach Keskin in there, who's doing some really interesting work looking at remotely detecting avalanche activity. In this image here, we can see a couple of things. You can see those red crowns that were the same as the one in the image before. And then we can also see these blue polygons. Part of what Zach's doing essentially is looking at taking satellite data, looking at different passes of the satellite. So the satellites are orbiting the Earth, and you're trying to pick out data from before an avalanche cycle and after an avalanche cycle. And then you look to see how the snowpack on the ground responds to radar that you're sending down to the ground, and watching that response back up. And what you can see is that there's an increase in density, which where the debris piles are, which means that there's an increase in backscatter, or the amount of radiation, electromagnetic radiation that is being received by the satellite. There's more than there was before, and because of that, we can pick out these areas where there's an increase in backscatter and correlate them to avalanche activity, which is really pretty fascinating. The right side of this image is kind of the range front. You can see those are the areas that we were able to get into and see visually. You can see that the red crowns kind of indicate that, and then there are a lot of associated piles of debris below those crowns. And then on the left side of the image, the west side of the image, you see just debris pile after debris pile at the base of these big chutes here. As far as the avalanches that occur, there were some interesting characteristics to many of them. A lot of things just had pretty odd looks to them, pretty unique features, lots of ragged crowns, and debris stalled out on bed surfaces. So instead of having nice crisp crowns and then debris is slid down the bed surface, it gets kind of stuck on the top and doesn't actually rattle its whole way down. We were seeing widespread rockfall, a lot of cracking off into the base of the snowpack, a lot of kind of shattered slopes. Hard to describe it any other way than that, but these slopes that just seemed like they'd broken like a piece of glass, dropped on the ground. We saw a lot of slab activity on very steep slopes where you often don't see slab activity, where you're more likely to see kind of loose activity or no activity at all. And then lots of middle elevation crowns in paths that don't frequently produce avalanches, often because they're down in lower and middle elevation terrain. There's not as much wind, there's not as much snowfall down there, and so you don't see avalanches activity as frequently. We'll quick look through a few photos of some of those features to maybe help you get a little bit of a sense of that. This photo gives you a pretty good sense of these kind of ragged crowns that we were looking at. This is a east-northeast facing slope. We're almost 45 miles away from the epicenter of the earthquake. You can see in a few spots that the avalanches actually stepped down from just the storm snow into some layers of crests and facets that formed during some of that dry periods of dry weather in January. Here's another view you can make out up near the top. There's some pretty obvious avalanches and some of that alpine terrain where you'd expect to see them, that terrain where wind is playing a predominant role and you're building these big slabs. But what you're also seeing is these down near the bottom of the image, there's crowns on all these low elevation slopes where you very, very rarely see crowns. And it's pretty hard to explain how you might get avalanche activity in an area like that in the absence of an earthquake. Here we're looking at a steep peak in the Sawtooth. This is a coveted ski line. The top of this is a little steeper than 50 degrees, and just down from the top there, you can see this really ragged crown that cuts across the entire face. Pretty unusual sort of feature. One of our Avalanche forecasters, Chris Lundy, who's been in the area for quite some time, has only only recalled seeing slabs on this face, once or twice. And even then they really didn't have this sort of appearance to them. Here we are, we're looking about northwest in this image, and you can see this is kind of one of those shattered slopes that I was telling you about. And the interesting thing about this is you see these interesting offsetting cracks. So you have these first set of fractures that are roughly sloped parallel, the ones that run from the upper left to the lower right in the image. And then where I've kind of highlighted with these orange or with these red dotted lines, you have these fractures that actually offset those cracks. So you know that those first set of cracks were established, and then somehow the second set of cracks, which run nearly up the slope in this area, offset those cracks. We saw a lot of deep cracking in the snowpack. In this image, you can see some of these kind of slope parallel cracks that run all the way across from lower left to upper right, as well as a few pockets on the right side of the image and on that left side there as well, where we've actually initiated fractures and had avalanches on a bit deeper layers in the snowpack. And unsurprisingly, we also saw a lot of rockfall associated with this. This is a pretty interesting shot here. Those are the Hansen Lakes at the bottom there. It's kind of the north end of the Sawtooth. And you can see this dust, the remnants of the dust cloud kind of on the right side of the image there. So the earthquake generated this or caused this big rockfall, and then the dust cloud spread out, and the record of that is indicated in the snow there. And here's another look at some rockfall. It's pretty widespread. We were finding rockfall really all across the range. And up there in that upper left there, you can see this feature known as Barren Spire. I'm going to pull back to that in a second. You can see it's awful pointy in that photo, and it's a little less pointy now. So after an earthquake occurs, we have a sequence of what are known as aftershocks. And really, it's best to think of earthquakes and aftershocks as kind of a singular event. You have a main shock, and then the series of aftershocks that follows. And the aftershocks are actually moderately predictable. We know if we have enough data going back in time on a given fault, we can make some sort of estimate of how many aftershocks we might see and how large those aftershocks might be. Here we are looking at a map of the area. There's the town of Stanley indicated. The large red circle with the dot in the middle is the epicenter, and then all these other circles are locations of aftershocks. As of about a couple hours, we've had over 2,000 aftershocks, and 16 of those are magnitude 4.0 or greater. Those large aftershocks you could feel them. In the town of Stanley, residents are feeling nearly every one of those aftershocks, provided they're not moving around or in their car or something like that. And it's fairly obvious when they happen. They move the ground, and it's pretty easy to sense. In August, there was a aftershock that triggered a pretty significant rockfall in the Sawtooth. I'm gonna try to play a little video of that for you here, and then also censor out some inappropriate commentary. We'll see how this works.
Look at your rock. Dude, the rock is Smoothie's gone off the top! Smoothie's gone! Smoothie came down! Smoothie is gone! Is that the one that we're gonna climb tomorrow? Smoothie is gone!
Okay, I think I successfully censored that. My favorite comment on there isn't the loud "Smoothie is gone," but if you watch it a few times, there's a guy in the background who kind of cautiously asks, "Is that the one that we're going to climb tomorrow?" Clearly, these aftershocks have an impact on the. Oh! There we go. Clearly, even these smaller aftershocks have an impact on the land service and on the ground service, and there's something that I really hadn't spent a lot of time thinking about until this earthquake event occurred. We know there's a predictable empirical relationship between these aftershocks and the main shock itself, and so we can say for a given earthquake that there's going to be approximately X number of aftershocks on that fault. We've actually reached that number now. I think it was 15 was the prediction, and we're up to 16. But certainly something to think about as you move forward when an event like this happens. For instance, if this had happened not in March at the end of the season, but in right now, maybe in December or in October or November, and you knew this aftershock sequence was going to be occurring while you were issuing avalanche forecast or while you're traveling in the mountains, it's certainly something that you should be aware of. This map here that we're looking at is produced by the USGS, U.S. Geological Society, and it's what they call their National Seismic Hazard Map. It's based on the history of past earthquakes, how much ground shaking the past earthquakes have produced, location and distribution of faults, and how rapidly the earth deforms in response to tectonic forces. What I'm going to do is overlay the boundaries of all the avalanche centers in the U.S. here, and you get a sense for how many of us might be dealing with this problem, particularly in this Intermountain West area. We're seeing a lot of orange to yellow colors, which has given us, well over 50% chance of damaging shaking in 100 years. And where you guys are over in the Northwest, up here in the upper left, obviously you're even a bit more likely to encounter that sort of thing. And same down here in Seattle, or excuse me, down in California. So what do we do with all this? Well, there's a lot of questions here, and there aren't that many answers. And a big reason for that is that we're dealing with something that's just incredibly hard to study. Avalanches themselves occur in remote, rugged, mountainous environments. Conditions are challenging to deal with. It's cold, it's dangerous, and earthquakes. Many of the same things are true. And so now we're trying to study something that occurs at the overprint between one somewhat unlikely event and another unlikely event. And so we just don't have that much data to look at. But there are a few real obvious questions that come to mind, and that have come up in the course of this work, and that many people often suggest. First, how does an earthquake affect stability in the hours and days following the earthquake? We got a lot of this immediately after the earthquake happened. A lot of questions about this from our users, and totally fair question. The answer to this, and probably the rest of these, is really, well, we're not really sure. Nobody really knows. I think intuitively, any slope that survived the earthquake, that was able to be shaken like that and then is still there, is probably at least as stable as it was before. But again, I'm saying probably, and I'm saying at least, and I'm saying likely. These are all words that indicate that we really don't know. And in the case of this earthquake, it occurred, near the peak of intensity in the storm, but it snowed for a few hours following this, and the wind blew, continued to load slopes and build slabs. So there's no real way to say that yes, the stability is better now. You can go out and travel in the mountains safely. I know for me, particularly in any steep terrain, I just avoided for the remainder of the season. One part of that, avoiding these really steep, beautiful couloirs that the Sawtooth are famous for, is just being aware that you have this ongoing aftershock sequence, and you probably have all these bits of rock that have been rumbled, moved and shaken, and are in perhaps more unstable conditions than they were before. Another question been hearing a lot is, what size of earthquake is needed to trigger an avalanche? And again, that's a big, well, it depends. Well, we don't know exactly. If your snowpack is entirely stable, for instance, if this event had occurred 3 days before, when we had basically a stable snowpack, I don't think we would have seen anywhere near as many avalanches. It seems almost certain. Also, if we hadn't gone through that big deep slab cycle in January, it seems relatively unlikely that we would have, or it seems that likely that we would have seen many avalanches breaking on deeper weak layers, which wasn't something that we saw a whole lot of. Third question been getting a lot of is, how many of these avalanches occurred? How many of the avalanches that occurred would have failed without the earthquake? This kind of ties back into that other question, but it's just really hard to say. We did some work trying to make some sort of sense out of which avalanches had failed because of the earthquake and which avalanches had failed naturally. And really, there wasn't a lot that we could do to tease those signals out. I think we can say with pretty high certainty that a number of these avalanches definitely failed because of the earthquake. There's no real doubt about that. But as far as pointing at an individual one and saying this is an earthquake avalanche and this one's a pre-earthquake avalanche is really hard to say. In addition, we had a pretty large magnitude aftershock. I think it was, I believe, a 4.8, just a half hour after that, after the main shock. So who knows how that plays into that as well. It changes the appearance of the debris of these avalanches. It changes the appearance of the crowns of these avalanches. Really, we're in a situation where we have far more unknowns than we have knowns, and there's that makes it a pretty tricky situation to deal with. So I don't have a whole lot of answers for you, but we have all sorts of things to think about, and particularly think about moving forward as events like this continue to occur, as they're inevitable to do so. Got a lot of help from a lot of different really smart, really hardworking folks listed here. Big thanks to everybody who's contributed to this. Thanks for the Northwest Avalanche Center for putting this on, and for everybody for tuning in. So without any more delay, I will turn it back over to Scott.
Yeah, Ben, no, that was really fascinating. One of the questions that came in from a guy named Kevin that I kind of had the same question was when you were out, did you actually feel the earthquake or experience like the shaking? Like, did you know what it was, or did you feel it, or what?
I was driving back when the earthquake happened, so yeah. I did not feel it. It had only been, it was maybe an hour and a half drive up to where I had skied that day, and I was halfway back when the calls started rolling in. So I was driving when it happened, but I'd been, I skied till almost dark that day, obviously mindful of the terrain I was in, and it was a high danger day, so I wasn't entering avalanche terrain. But yeah, unfortunately did not actually feel the main shock.
Yeah, I was wondering, like, if it knocked off a bunch of the new snow out of the trees or anything like that you'd noticed, or.
Yeah, it wasn't, I didn't notice anything until the text messages started rolling in. Till my phone digged about 20 times, and then I kind of started to wonder what was going on.
Yeah, I have a distinct memory. I was back in 2001. We had that an earthquake that was 6.8 outside of Olympia, and I was actually skiing up in the Alpental Valley when that happened. It was in the morning, and feeling the seismic waves was quite a trip. And there was a little bit of snow in the trees, and the trees were moving around, and it was kind of a surreal experience. So yeah, so it definitely backcountry skiing and earthquakes do collide, I suppose.
Right. Yeah. One of the forecasters who works for us at the Sawtooth Avalanche Center, Chris Lundy, was out in the mountains that day. He was out at one of the huts, actually.
Oh, wow.
And, he was able to, he felt it start, and then he was staying up there with his wife, and they both poked their head out, and they're watching snow falling off the trees. And you could actually hear residents of Stanley reported that they could hear the rush of avalanches following the earthquake for minutes.
Wow.
So there was, there obviously was a major response to it, but depending on where you were, you either, you felt it or you didn't.
Yeah, right. Yeah, exactly. Yeah. A question from Andrea here. Any thoughts on earthquakes improving stability?
We got a lot of questions about that, and I kind of tried to touch on that first question, but I think, intuitively, you think anytime you put some sort of big signal into the snowpack like that, if it doesn't respond, likely as time passes, stability is improving.
Right.
But that's kind of there's a whole lot of likelies, and it seems like, and that sort of thing in there. Yeah. And yeah, and obviously we get, there are lots of incidents of post-control releases in ski areas where people are, they're putting a signal into the snowpack. It's not an earthquake, it's throwing a bomb at it. But, you go through this step that tells you, oh, it seems like, stability is improving here, or, it's at least it held up to this. And then you have an avalanche that occurs on those sorts of layers. So
Yeah.
I think with it's hard to say with any sort of confidence. And I certainly personally would not use that to direct the way that I traveled in the backcountry.
Right.
Yeah.
That makes sense. Matt Henry's got a question. He's wondering how he might be able to find out about aftershock swarm predictions, like info. How do you, if there is an earthquake, is there any tools or resources?
The USGS maintains a really cool database online showing recent earthquakes, and they have it all cataloged back through their entire database. So that's a good way to look at that and follow stuff as it happens. Like there's that big quake that just happened up in Alaska, and I think they've been like 10 plus magnitude magnitude 5 or greater aftershocks related to that. It was the main shock was a 7.5.
Wow.
Yeah, so it's kind of a neat way to watch stuff happen. Yeah.
But one of the questions I had regarding I think one of your initial questions that you were posing after this was, did any of you or any of your forecasters have an opportunity to go out and perform any snow stability tests prior to did you have any snow stability tests you'd looked at a particular site in which you could go back right after the earthquake and see if there was any difference in results?
Yeah, that's a good question. Since most of the avalanches involved only the new snow, and we really, when I was out there that day, I wasn't performing stability tests because it was fairly apparent that stability was quite poor. Like stability tests weren't important to me at that point. Weren't really guiding our stability assessments. And then after that, no, I wasn't doing. I hadn't done any stability tests on that new snow, but I think. Yeah, I suspect maybe you would have had more interesting results if you were dealing with a buried persistent weak layer that you could maybe you'd been tracking, and then you see that there's this big change in your stability test results. But given that it was all snow that had fallen in the last 36 to 48 hours, it wasn't really. We don't have good data on that. Yeah, it's a good question though.
Yeah. Elise is asking here, is there any way to simulate this sort of an event in a computer model? Wondering if there's ways to collect more data and or make more observations for such a rare event?
I suspect that there is some way. I mean, I'm not the correct computer guru to ask, but I also suspect that. There's a huge amount of effort that's going into modeling avalanche release right now. And then there's obviously a lot of effort that goes into engineering for earthquakes and those sorts of things. So I suspect you could try to overprint those two, but they're just such complex events in singularity. Each one is so complex that you're dealing with so many unknowns that, I'd like to see somebody try, that's for sure. Yeah. I don't know what the outcome would be. Yeah.
Yeah, totally. Elaine is asking if this is published or any way that, do you have a paper or a presentation that someone can download?
Currently no published work, but working towards some sort of paper on this. And then I suspect I will do a similar presentation for our local audience that will be available in some form on our website. But
awesome. Great.
Yeah.
And then let me see here. Yeah, Charlie Rubin. Hi, Charlie. He's kind of reaching out and saying, super interesting talk. If you're interested, he's got photographs from a large earthquake, 7.9 up on Denali in the Alaska range. Lots of photographs from the ground and helicopter. So
yeah, have him reach out. My email is ben@sawtoothavalanche.com. I'd be happy to hear from anybody. I've had a lot of folks who have kind of relayed similar things. They were in an area where an earthquake occurred and seemed like maybe there was an avalanche that was triggered by that. This event seems to be unique in that it's unique in that it occurred in a forecast area for an avalanche center. It also occurred during peak of avalanche hazard, and we were able to go out and kind of document it. So a little bit unique in that sense.
Awesome. Yeah. Maybe final question here. How much avalanching did you see on, low angle, less than 30 degree slopes, start zones? less than 30 degrees.
It seemed like getting, as you got down towards 30-ish, that was where you were kind of transitioning between seeing widespread avalanche activity and just seeing that widespread fractured nature to the snowpack.
Right.
But really, it seemed like most of the snowpack that was steeper than, low 20s, mid 20s was just absolutely shattered by the ground shaking. And then as you approach flat slopes, obviously you don't have the gravity factor kind of offsetting your fracturing. So those fractures aren't as evident after they've fractured. They're not opened up like they do on steeper slopes.
Yeah, kind of like in line with what we might expect with regular non-earthquake induced avalanche activity.
Right. Yeah, exactly.
Yeah. Well, awesome, Ben. I think that's about all the time we have tonight for questions, everyone. Thanks so much for taking the time out and presenting. It's super interesting work, avalanches and earthquakes. I think we're in, as your map showed, we are in a hotbed area for that. So yeah, thanks so much, Ben.
Yeah, thanks a bunch for having me. It's been a privilege.